First of all, thank you everyone for coming. And yes, before I begin my talk, I should thank the organizers. It's a great idea. I'm looking forward to the other talks in the series. Now I'll be talking about periods and something about periods. I have something specific in mind, but let's just talk about what periods are and why we should care. And to do this, we should think a little bit about real numbers. And a surprising feature of real numbers is that actually it's impossible to compute with them in practice. And that's just a counting problem. So there are uncountably many real numbers. But if you view real numbers as algorithms that take in an integer, n, and produce its first n digits in its decimal expansion, you will see that, well, we can only write down countably many real numbers, countably many algorithms in this manner using finitely many symbols of finite length. So there's simply no hope that we can compute with real numbers. But we don't give up. Of course, we can say, well, perhaps only some of the real numbers are interesting anyway, and we should construct some countable subset of real numbers which captures all these interesting numbers. So these interesting numbers should come from nature in some sense, maybe physical constants and constants arising from geometry. And Kontsevich and Zagier suggest that we consider what they call the set of periods, or the ring of periods. So the real periods are expressed as integrals. The integrand should be an algebraic function. That means that this function should satisfy a polynomial with polynomial coefficients in many variables, perhaps. And the integral should be taken over a semi-algebraic domain. That means the domain should be cut out by polynomial inequalities. In other words, all of these integrals can be expressed using finitely many symbols, starting with integers and polynomial expressions. And of course, complex periods are just numbers whose real and imaginary parts are periods. And an example is, of course, pi. This should be a period. And I've expressed this as this integral where the domain is defined by x squared less than 1, so it's this interval. And the integrand is an algebraic function. It satisfies the polynomial y squared equals 1 minus x squared, for example. So if you plug in y equals the square root, you'll have an equality. So it's a period. And once you have such a formulation of your set of numbers, you can do one of the key things that you'd like to do, which is to check for equality. So you cannot check for equality with arbitrary real numbers using finite algorithms and finite time. But with this construction, you suspect that it should be possible. And here's how it should be possible. And this idea we will use later on. So if you give me A and B, and I want to check if A equals B, the general strategy should be like this. First, I define a function on the set of periods. And this is just a function. It's sometimes called a height function. It will go to natural numbers, but I want it to have finite fibers. That's its key property here, the only property that I care about. And then I can define a separation constant, which is a distance between periods of bounded height. So it's a function epsilon. It takes small h. It collects all periods, finitely many, of height less than h, or at most h, computes their differences and computes the norm. And it takes the minimum. So since there are finite many, this minimum exists and it is non-zero. And what you can do now is to say, all right, if you give me A and B, I could first compute the height of A and B. I evaluate this function epsilon if I can at that height. So this epsilon tells me how close A and B are allowed to come together without being equal. And then I start approximating A minus B. If my approximation of A minus B gets closer to 0 than the separation constant, then I conclude that A and B must be equal. So this is how you would be able to check for equality, except there's an exclamation mark here precisely because this epsilon exists, but we have no way of evaluating this epsilon. And well, this is an open problem when it comes to periods, to devise a strategy to effectively evaluate epsilon. And we will tackle a portion of this problem here. But let me mention the connection to geometry. So if you give me a smooth projective variety, let's say defined with over Q bar, then I can use this X to generate numbers again. And the way you do it is that you take homology classes in X, so you view it as a complex manifold, you get homology classes. You take the RAM classes, so cohomology classes, and then you integrate with the cohomology class over the homology class. So it gives a complex number, and it's a folklore theorem that this integral will in fact be a period. Something like the converse is also true, but I will not get into it, so that every period is geometric in nature. One thing I should point out that obviously homology classes are integral lattices, perhaps with torsion, so there are countably many. So there are countably many varieties, countably many homology classes. You have to be careful with cohomology classes. You don't want a real or complex vector space, so the classical formulation of cohomology or the RAM cohomology will not work. You don't want uncountable vector spaces. You don't want uncountably many cohomology classes. So this is an algebraic formulation of the RAM cohomology, which allows this thing to be a Q bar vector space. Well, that's a detail. It just means that I indeed have only finitely accountably many integrals, so that such an inclusion would make sense. Now, there's one more delicate feature here that connects us to geometry again, is that if I take a subvariety of X, then it will give me a homology class. And if I integrate forms over this homology class, I very often find 0. And it's because the tangent space of a complex submanifold lies in a very particular position in space, which means that most cohomology classes simply immediately vanish when you restrict to such a complex tangent space. And what survives is PP forms. So that's interesting because that means we have algebraic cycles allows me to express zeros, to express relations in a sense. And Hodge conjecture is a version of this, of the converse of this, that whenever you represent 0, it says there's an algebraic cycle. A more general version of it is called the period conjecture. So this is now considered to be at the level of science fiction. So we have very little reason to believe it. And it's a vast generalization of Hodge conjecture, which we still do not know. And very loosely, it says that if you have two periods, A and B, given in terms of two integrals, perhaps given on different algebraic varieties, these two periods are equal if and only if there exists an algebraic cycle in some variety defined over Q bar again, and somehow you can represent A minus B as an integral over this cycle. So, I mean, it's very interesting that on the left-hand side, you have transcendental number theory. You're trying to find identities between very complicated numbers. On the right-hand side, you have pure algebraic geometry. And this conjecture is a bridge between those two, much stronger than Hodge conjecture. And the way we've stumbled upon this area is because of a computational reason. So in fact, we can approximate these period integrals for hypersurfaces. So this is due to one of my older works, that if X is defined by a single polynomial in a projective space, so it's a hypersurface, then I can compute these periods. So I can approximate it to a desired degree of accuracy. And, and we can find integral linear relations between those periods. We can guess them with very high degree of confidence. So these integral relations are also called Hodge cycles. If Hodge conjecture is true, these Hodge cycles are algebraic. And what we want to do is that once we formulate our guesses as to what Hodge cycles are, so what relations evaluate to 0, we want to be able to prove that our guesses are 0. What we compute to be approximately 0 periods, we want to show that they're identically equal to 0. Okay, so I've been talking about this very this pie in the sky dream of making arithmetic effective for periods. But now what we're going to do is to restrict ourselves to a very small chunk of this problem, and then to solve this problem in this small chunk. Okay, so this chunk is periods coming from quartic surfaces. A quartic surface will be cut out by a polynomial, degree 4. And although I did allow at the beginning to have Q bar coefficients, our lives will be much simpler during this talk if we work only with Z coefficients. So throughout the rest of this talk, I will work with Z coefficients for simplicity. So now X is cut out by a polynomial with integer coefficients. And it turns out that, well, X is a K3 surface, and it has a one-dimensional space of holomorphic forms. So these are H2 zeros in the cohomology H2. So this space is one-dimensional, and it has, in fact, this canonical generator. So it's the Griffiths residue of a form, and modulo details, this volume form is on an affine charge, just dx, wedge dy, wedge dz. So this is really what you expect the volume form to be. And you divide that by f. So this is a form which has poles identically on x. And just like in univariate calculus, there's a notion of taking residues. But now residues are not numbers, but they are forms. And this particular thing has a residue, which is a holomorphic form on our K3 surface x. And if you insist f to be primitive, so no greatest common divisor of coefficients equal to 1, then you realize omega f is defined up to sign. So that's a neat feature. Now what I call the periods of x is simply the set of integrals of omega over two forms in x. And what you should notice is that since I can add and subtract homology cycles, I can also add and subtract periods, and that will still be a period. In particular, if I want to check if a period A equals a period B, then all I have to do is to check whether or not the period A minus B equals 0. So the game here is to be able to determine which of these integrals are identically 0. And this is given to us by Lefschetz 1-1 theorem. So this Lefschetz 1-1 theorem replaces this humongous period conjecture. So this is now a simple theorem, something we know to be true. And it says that one of these integrals, any of these integrals is 0 precisely when the domain of integration gamma is algebraic. And if you want to think of curves on surfaces, then you can say gamma is represented as the difference of two effective cycles, each cycle being the homology class corresponding to a curve, possibly non-reduced or not irreducible. Okay, and so this is also very interesting because on the left-hand side, we have numbers without context, almost something transcendental. On the right-hand side, we're talking about curves on surfaces. And whether or not a curve lies on a surface is really a condition is a polynomial condition on the coefficients of f defining x. So here we connect transcendental number theory very explicitly to algebraic geometry, to polynomials. To make this a little bit more explicit, now let's think about how one could think of these things as from a computational point of view. So let's choose a basis then for a homology group. That's a 22-dimensional lattice, and I choose gamma 1 through gamma 22 as a basis. I define the period vector of x to be the integral of omega f over these 22 cycles. So this is a sequence of 22 complex numbers. For instance, the Torelli theorem says for K3 surfaces that this period vector determines x up to isomers, which means this period vector knows everything there's to know about x. Also, the set of periods is completely determined by this vector. You just take integral linear combinations of these 22 complex numbers and you get all possible periods on x. And Lefschetz 1-1 theorem writes as saying that the Picard group of x, so algebraic cycles on x, is identified with the kernel of this vector, this matrix, from Z22. That means that I take 22 integers, I take the dot product, and that gives me a complex number. Whenever this dot product is 0, then this A is in the Picard group. So it's A defines an element in the homology group that should be algebraic. So what I did previously was to be able to approximate these period vectors for hypersurfaces in general, and what we did with Pierre afterwards was to be able to not only to be able to guess this kernel with high degree of accuracy, but to also understand what is the nature of the failure if we do fail. So but once you approximate PF and you can guess what the kernel of this should be, there are methods to be able to do that. you will have a lattice, this kernel, and for a generator of this lattice, you will know that P dot A is approximately 0. And now the question is, can we say it's identically 0? You know, how do we do this? How well do I have to approximate this thing which I suspect to be 0 so that I can conclude that it is identically 0? And here we draw our inspiration from algebraic numbers. They have a measure of height, which allows you to compute separation bounds between algebraic numbers. So when alpha is an algebraic number, you can define the minimal polynomial of alpha. You can also take an approximate rational complex number approximating alpha to determine which root I'm talking about. Or if you want to be a little bit more crude, what you can do is to take the degree of P and the norm of P. And by norm of P, I mean the maximum of the absolute values of the coefficients of P. So you have a pair of integers, and these pair of integers capture how complicated alpha is. And with these pairs of integers, you can compute these separation constants. Okay, so we want to do something like this. The analogy is drawn from, it's like this. So for an integral, for a period, I say, okay, f looks like a polynomial, maybe I take this. Gamma is like a root, maybe. This is not quite nice because gamma is a homology class. It's just too flimsy. It's not good to work with. So instead, we make it a little bit cruder. And to gamma, I associate what's called, I associate an integer instead. And this integer is called the discriminant of gamma. And I can also take the norm of f if I want to make it simpler too. So the discriminant is expressed as the degree of gamma. So this is the hyperplane class of x. Gamma intersected with the hyperplane class. This is the degree of gamma squared minus 4 times the self-intersection of gamma. So this is the discriminant of a 2 by rank 2 lattice generated by the hyperplane class and gamma. Well, it's not important what it is, where it comes from. It's just a very easy thing to compute, a simple, robust integer, not a flimsy object like a homology class. To gamma, to delta, I associate now another polynomial. To delta, I associate first the hypersurface in the space of quartics. The space of quartics is a P34. It's a projective space of dimension 34. And the Noether-Lefschetz locus will be the set of quartics which have an algebraic homology class, which has discriminant delta. And in general, this is a hypersurface. If not, it's empty or everything. So it's cut out by a polynomial P delta. It in fact has integer coefficients in 35 variables, and it has a degree, which I will call D delta. And our first theorem in terms of these P deltas says the following. So there is an effective constant, which I will give in a second, epsilon, that depends on delta, and to make it nicer on f, such that a period is either identically 0 or the absolute value of this period is bounded away from 0 by epsilon. So that now gives us a method to check whether a period is 0. You just start approximating it. If it is actually 0, once you approximate it well enough so that your approximation says it's smaller than epsilon, you may conclude that it is identically 0. So it's an algorithm, if you provided you can evaluate epsilon. And epsilon here is like this. So the reciprocal of epsilon is 3 products. On the last 2 products, I just want to point out that there is no delta. So you compute it once for f, and then you put it aside. And if you can compute the periods of x, and we can approximate them, then you can easily compute these 2 numbers. So that's all I have to say about those 2 numbers. So they don't matter. What matters is the first parenthesis here. So you see the degree of the Noether-Lefschetz occurs, the height of the Noether-Lefschetz, and essentially the height of f to the power of d delta. So here the degrees grow, the heights grow, there's a factorial here. So this first factor will be astronomical, which means epsilon will be very, very, very small. So I said the last 2 factors are easy to evaluate. Height of f, nothing to it. The degree, I will talk about it in a second. We can compute the degrees, which leaves that provided you can bound the height of the Noether-Lefschetz loci, the polynomials p delta, then you can evaluate epsilon, which means you can execute this algorithm that I mentioned before. Okay, so now it's time to talk about the degrees. How do we compute them? And this is a theorem due to Maulik and Panderbande. So it's a spectacular paper. It connects Gromov-Witten invariants to these Noether-Lefschetz loci. But the part I want to take from it is that they give they write, let's say, a power series whose coefficients store these d deltas, these degrees of Noether-Lefschetz loci. And they say that this is essentially a modular form. And modular forms have finitely many generators, so you can, they figure out exactly which modular form it is. And this allows you to compute the first million degrees in a few minutes with a computer. So it's very, very explicit. That's what I want to say. And also, if you want to say how these degrees grow as delta grows to infinity, then you can just fiddle around with these modular forms and see that how their coefficients grow. So here's a very crude bound, which says there's this polynomial growth on the degrees. Okay. Now I need to tell you how to bound the heights of the Noether-Lefschetz loci in order to make theorem 1 effective. And here, this is our contribution also, it says that the height of P delta is bounded by this rather ridiculously large number. It's triply exponential, so 2 to the 2 to the 2 to the 21 cubed delta cubed. Now, unfortunately, this causes a problem. There's no way I'm going to compute anything to so many digits and to be able to use theorem 1 in practice now. However, it does make our theorem, and together with the theorem 2, it does make our numerical approximations into an effective algorithm. So it's now theoretically effective if you had an enormously powerful computer. And these bounds are extremely pessimistic. So provided someone came up with a better idea to approximate these things on the nose, then I suspect the growth will be much, much milder. And then actually there's room to make these algorithms in fact, practical, not just effective. Okay, but we do make the most of what we have, and we also make the following conclusion, which is we write down a number, which we say cannot be the ratio of two periods of a quartic surface. Again, theorems like this are very hard to come by. People usually study periods of curves or periods of abelian varieties. These have sort of level 1 in some sense, and level 2 periods, so periods of surfaces, they have not been exhaustively studied. Okay, so this is a new kind of result, which says, okay, this number is not a ratio of periods, and I should say what this double arrow indicates. And this double arrow is Knuth's tetration. It says, write a power tower of 2s, and this power tower should have height 5 to the n. So I'm going to write 2 to the 2 to the 2 to the 2 to the, and there will be 5 to the n many 2s in this tower, and then I will reciprocate and then sum. So this is a hyper-super Liouville number, and we claim it's not a ratio of periods. So in the remaining time, what I want to do is to prove these, or sketch the proofs of these theorems from the easiest to the most elaborate. And I think this is a good time to ask questions if there are any.
Any questions? As it seems there is no Emre. So
right.
Please just go ahead.
Okay, so let me remind theorem 1 again. So theorem 1 says that if a period is sufficiently small, it's identically 0. Theorem 2 allows us to make explicit what this sufficiently small means. And theorem 3 is going to exploit these two facts. And I'm going to start with the proof of theorem 3, which follows from theorem 1 and theorem 2. So I gave this infinite sum using Knuth's tetration. And let's denote this infinite sum by alpha. And let's suppose this alpha is the ratio of two periods to derive a contradiction. So this alpha was an infinite sum, so it has partial sums. And if I sum the first n terms, I get a rational number, and I'll write this rational number as Pn divided by Qn, relatively prime. So these rational numbers approximate alpha, and they approximate it very, very well. So by design, so these Qn's go to infinity very quickly. And well, you can see that the difference is bounded by the reciprocal of the denominator of the next term. And so this Qn plus 1 is going to be much smaller than Qn because of the nature of the number alpha. And if I clear the denominators here, so I multiply by Qn and write it again. So I multiply by Qn. I also multiply by this integral at the bottom. So I have a single expression here. Or I can write it as the integral of omega over 1 integral cycle. Now that is bounded by some constant, this integral times 2 times Qn divided by Qn plus 1. So what's happening here is that as n goes to infinity, this ratio goes to infinity so much faster than, well, it goes to 0 so quickly that it beats the rate at which epsilon goes to 0. So here, epsilon of this integral cycle that I'm using here. But that means that by theorem 2, eventually, the left-hand side being smaller than epsilon must be identically 0. So here I use theorem 1. And well, that's a contradiction. The partial, this left-hand side cannot be 0 because the partial sums are never equal to the full sum alpha. And so this is how you can do transcendental number theory essentially with these geometric notions. Okay, now let's talk about the main engine behind these ideas. And this is theorem 1. So here for theorem 1, I'm just going to give a picture, a proof by pictures if you want. And here, what we're going to do is to put two competing forces against one another. And one of the forces is this, that I said that Noether-Lefschetz locus delta is the locus of quartics which contain an algebraic cycle with discriminant delta. On the other hand, gamma is algebraic if its period is 0. So gamma has discriminant delta. That means that the period of gamma should be some measure of proximity of f to the Noether-Lefschetz locus. And so you have to work a little bit to understand the exact constant in front of this period so that really it gives me the distance of f to the Noether-Lefschetz locus or a bound of this distance. But yeah, so that's one component. The periods bound the distance of f to the Noether-Lefschetz locus. To do this, actually, you have to understand the period map from the space of quartics. What we did was to study the power series expansion of the period map at f and to understand the growth rate of the coefficients of this power series. And this required the study of what's called the Griffith-Dwarf production. And once you have a power series and you understand the growth of the coefficients, you can use Smale's alpha theory to understand how a map distorts distances. And that's what we do. Okay, so this is this blue part, this blue region is a ball defined by your approximation of the period. It tells you where f is relative to the Noether-Lefschetz locus. And on the other hand, the other ingredient we are going to use is something that says f cannot be very close to the Noether-Lefschetz locus. And to do this, we recall that I assumed f has integer coefficients. If it did not, you can understand how to modify this argument. But also the polynomial defining the Noether-Lefschetz locus has integer coefficients. Now, if I evaluate this polynomial on the coefficients of f, it's an integer, and this integer is either 0, that means f lies on the Noether-Lefschetz locus, or this integer is, has norm at least 1. And this jump from 0 to 1 tells you that f is either on the Noether-Lefschetz locus or it's pushed away by a certain distance, which depends on the height of p and the height of f. And f is pushed away from this, what I call this arithmetic repulsion zone. And it's easy to compute the distance of this zone, the thickness of this red zone in terms of these heights. It's a Taylor series expansion to one term. So it's a very simple argument. Okay, so now it's clear what we're trying to do. I just approximate this period. If it's actually 0, and I don't know it, but then my approximation should converge to 0. And what is sufficiently close to 0, this blue region will lie entirely in the red region. And now I will apply the other argument that says f cannot be on the red region unless it lies on the Noether-Lefschetz locus. So these are the two competing forces. You put them together and tells you that, okay, the period is either identically 0, it's bigger than some epsilon. Okay. So now what we want to do is to compute the height of the Noether-Lefschetz locus. So I have no means of describing the Noether-Lefschetz locus. I gave a geometric modular description of this Noether-Lefschetz locus. It does not tell me what kind of polynomials would cut it out. So what I need to do is to find something whose equations I can write down, and then to relate that object to the Noether-Lefschetz locus. And this is what I'm going to do next. And this is theorem 2 now. Theorem 2 was a bound on the height of the Noether-Lefschetz locus. So the first thing is I'm going to use curves in space to do this, and the Hilbert schemes of curves. And the first thing I do is that I say that if a very general element of the Noether-Lefschetz locus it will be a quartic of rank 2, and you can then just fiddling around with the rank 2 lattice, you can figure out a genus that's roughly the size of delta, and the degree of that's roughly the size of square root of delta. So you can find the genus and degree such that there exists a very ample curve in this very general quartic in this Noether-Lefschetz locus of degree d and g. Because it's very ample, now I can compute the size of the linear system. That will play an important role. Okay, so for curves of genus G and degree D in P3, I have the corresponding Hilbert polynomial defining those schemes. And I define the relative Hilbert scheme, which is a pair. So it's a quartic, or the polynomial defining a quartic, and the ideal defining a scheme, which has this Hilbert polynomial P. So because of the shape of this polynomial, this ideal will cut out something of dimension 1. Not necessarily pure of dimension 1, but dimension 1. And if the corresponding curve is inside of the quartic, if the polynomial f is inside the ideal I. And what's true is that, in fact, you can write down the equations for this Hilbert scheme. So this is the work of many mathematicians going back to Grothendieck, and the ideas have been refined ever since. So we use the ideas of Gottman, which makes it explicitly, especially easy to write down these equations defining H. And so where does this H live? It lives, first of all, in the product of the space of quartics times some Grassmannian. So this Grassmannian will be capture the degree R part of I, but never mind that. So what's important is that this Grassmannian lives, of course, in another projective space. The space of quartics is a projective space. So the Hilbert scheme lies in the product of two projective spaces, and I have equations on such a product. So here, R is very special. So I'm saying that I'm looking at some degree, a certain degree R part of I. And so that's due to Gottman that you can do this, that you can recover the ideal from just looking at the appropriate sufficiently high degree part of an ideal. And so NR here is the dimension of degree R polynomials, and PR is this dimension of IR. Okay, so it's a explicit construction. All right, so a couple of things about Hilbert schemes. They're extremely nasty. They have many components that do all sorts of things that you would not want them to do. So that's the trade-off. You have explicit equations, and in return, you have something horrible. Now you have to fix that problem. And that's one of the reasons why I took a very ample curve. At least what I know is that on each component of the Noether-Lefschetz locus, there will be a component in this Hilbert scheme, and I will know the fiber dimensions of these Hilbert schemes. Now, right, so how do I compute whatever that means, the height of a high codimension object like this Hilbert scheme and a product of projective spaces? And how would I translate it to the height of the Noether-Lefschetz locus? So it turns out that the general machinery for this has been built. And this is, it's a very interesting generalization of degrees. So for degrees of varieties in projective spaces or products of projective spaces, of course, we have a well-built notion of degree and how is the interplay between when you intersect hypersurfaces, how does the degrees change? They just multiply. That's Bezout's theorem. And the general construction for dealing with degrees is the Showring for products of projective spaces. And it turns out that there's an arithmetic Showring, which allows you to keep track of heights as well as degrees. So now let's this capital P be the product of these two projective spaces. In general, the work of D'Andrea, Crick, and Sombra defines what they call an extended Showring for an arbitrary number of products of projective spaces. So for the product of two projective spaces, P, I have three generators. So one generator, eta, that's the magic generator. That stores heights somehow. That comes from spec Z, if you want. So everything is defined over Z. So there's these things live over Z, and Z is one-dimensional. So that has its own generator, if you want to think of it like that. Theta 1 is the hyperplane class pulled from the first factor. Theta 2 is the hyperplane class pulled from the second factor. And so they construct this ring with the only obvious relations, and eta squared being 0. So Z pretends to be P1, and its hyperplane class, if you can call it, is eta squares to 0. The one extraordinary feature here is that the coefficients of elements in this extended Showring must be real numbers, and these numbers will in general be transcendental. All right, so what you have is that given a subvariety in its product of projective spaces, if it's defined over Q or defined over Z, you can associate to it a class in this Showring, so essentially a polynomial with each monomial being in terms of eta, theta 1, theta 2. You associate this polynomial, and what it does is that for any monomial that does not involve eta, it will store the honest by degree. And for every term for every monomial that does involve an eta, you'll have a strange number. These strange numbers are called mixed canonical heights of Y. There's more than one height, by the way. For a polynomial, I said I gave you one height. Look at the size of the coefficients, pick the largest one. So here, for something of higher codimension, you will have many different heights, and you will need to account for all of them. Okay, so this is a very, very long story. This paper is 70, 80 pages long, builds on their previous work whatsoever. So this is a deep work by them. Okay, so but I summarize these 80-page paper with 4 bullet points. These are the key properties that you need in order to work with these extended Showrings. The first thing is that if you have an effective cycle, so you really start with a subvariety, then the corresponding element will have positive coefficients. But what that allows you to is that if you have something such as our Hilbert scheme with many, many components, and you can bound its coefficients, I can freely remove any components that I don't want from it, and my bound for H will also bound any one of its components. So I can freely remove components. That's a very important feature. Moreover, I had a Hilbert scheme, and that thing lied over a Noether-Lefschetz locus underneath. Now I'm interested in the height of the Noether-Lefschetz locus. What they prove is that if you project something, then the heights can only decrease. That means if I can bound the heights of components of the Hilbert scheme, I can bound the height of the Noether-Lefschetz locus. So there's one more subtlety here, but I will not get into it. And then the other thing is that, of course, for a hypersurface, which is cut out by a single polynomial, I better be able to evaluate the corresponding class. And this is indeed true. For a hypersurface, it's codimension 1. It will be something eta times something theta 1, something theta 2. Coefficients of theta 1, theta 2 are the degrees. And the coefficients of eta is what's called the Euler measure of this hypersurface, but it's easily bounded by and bounds the coefficients of the polynomial. Okay, so we get in touch with the coefficients of polynomials, and finally we have something like a Bezout theorem. So Bezout theorem is usually just about the degrees, but essentially it's about products in the Showring. So, and now the arithmetic Bezout in this Showring says that if you take the intersection product of two cycles, if it's a proper intersection, then that intersection can be bounded by a slightly modified version of the corresponding cycles for X and Y. So it's not this on the nose, but it has to be slightly modified, but it's also a very easy modification. Okay, so now together with these four rules, I compute for you the height of the Noether Lefschetz locus. First was the equations for the Hilbert scheme are easy to write down by construction. And now that means the Hilbert scheme lies in the intersection of many hypersurfaces. Each of the heights of these hypersurfaces I can compute by rule 3. By using arithmetic Bezout, I bound the height of the Hilbert scheme. And then I can throw away the components that I don't care about because of item 1, that the components I don't want merely make the heights larger, not smaller. And then finally, I project what I have so that they land exactly on the Noether Lefschetz locus and they don't cover the entire space. And by item 2, the bounds upstairs were bound still for the Noether Lefschetz locus. Yeah, putting these together, this gives you theorem 2, which, by the way, it's the nature of arguments of this nature that you get these enormous bounds, these power towers. Okay, and I'll stop here and take your questions. Thank you very much.
Thank you very much, Emre, for your nice talk. Any questions?
Feel free to ask simple questions like, what is a polynomial?
Yes.
So,
Right.
yeah, sorry to ask a somewhat vague question. I'm just wondering, is it possible that there could be a non-Archimedean analog of these results?
Oh, you mean for p-adic periods?
Yes.
Oh, yes. Right. So in the p-adic world, you have one advantage. I suspect so. I have not done it, and I want to do it. Or, yeah, I mean, I haven't started. So if you want to talk, we can talk later. But so I can tell you there's one advantage for sure, which is that usually when you do a mod P reduction of your hypersurface, then there you can know the algebraic cycles on the nose. You won't be just vaguely sure, right? You know, which means that you overcome this problem. So you overcome this problem where you're not even sure whether your F is on the Noether Lefschetz locus. You know that mod P, whatever that means, mod P, you're on the Noether Lefschetz locus. So it kind of makes it even easier to get this epsilon bound, because you can avoid all the complex analysis that we had to do to get this epsilon. So you have a solid footing. And if your Quartic had only one algebraic cycle, which means that if I was in this situation denoted in this caricature, where F is near or sort of mod P on a smooth point of the Noether Lefschetz locus, I think then you're set. You can figure out to what degree of precision I need to compute the p-adic periods. And so this is essentially a deformation theoretic problem. From mod P, you have an algebraic class, you try to figure out its nth thickening and figure out whether or not it's still algebraic. So you just have to figure this out. And you can see what n you have to take there just by looking at this valuation of the coefficients of P. What I have trouble understanding is what happens when you're near a singularity. So it was still very easy to do in the complex world, as this singular locus is understood just by derivatives of P delta. So the multiplicity endpoints are cut out by nth derivatives of P delta. But to make sense of this and to get the right bounds, you really have to think over the complex numbers. I couldn't figure it out over the p-adic numbers. So, yeah, thanks for the question.
Any other question? So Emre encouraged also elementary questions that.
Yes, please go on.
Yeah. Also, here we have some students.
Oh, yes.
So maybe I can ask one.
Right, please.
About the theorem 3. So what's the specific about the numbers 2 and 5 here? Can we boil another example here?
Right, I can make these things larger, that's for sure. So this 2 is because of these tower of 2s. And the 5, so the 5, I mean, I wanted to have a nice number. And what I'm trying to do is that here in this power tower, you're actually evaluating the powers from the right. So it's not associative, this power tower. You have to evaluate from the right and they grow very large like this. In the proof where we're studying how Qn divided by Qn plus 1 grows, so this here, you have something like a power tower again, but now these power towers are evaluated like at 4 at a time or 3 at a time, something like this. And what I did was I wrote something which obviously defeated that power tower. So that was my only motivation, to make it very simple to write down the proof. So here I'm trying to defeat this number essentially, which is well used here. But yeah, that's it. Okay. I mean, much nicer numbers should be possible. So this is like a Liouville number. Its partial sums are extremely rapidly converging. For example, you know immediately it's a transcendental number. This is a theorem due to Liouville that any such thing must be transcendental. But it will be very interesting to understand better bounds for the height of P, not this triple power tower. I suspect, for example, the first P deltas have maybe 2 or 3 digits. This thing tells you that it has 10 to the 180 digits. You know, that's completely absurd. So with a better bound here, I'm sure you would be able to construct much nicer numbers. I don't know if that answers your question or if you have follow-ups.
It's okay. I see. I understand. Yeah, I mean, I understand what you aim to when you are constructing this example. Because I didn't see in your proof why you choose the 5. And I get
yes.
That.
Oh yeah. No, I don't think that 5 is super important. Maybe 4 would have worked, but this number was constructed when I was rushing to prepare a talk, and then I liked this number and kept it.
Okay.
But because I was rushing it, and literally I had one day, this was a couple of weeks ago, I must say, because I was rushing it, I wanted to just make sure that this thing bounds it, and I have made no mistakes. So probably 4 would work just as well here. 3 probably, maybe not. Maybe even 3 would have worked, but that would have thought that would require thinking, and I wanted to avoid thinking.
Okay. Other questions? Remarks? Well, seems no. So
maybe I can ask a question. I mean, it's
sure.
just a very late question, but the question. So, I mean, if you forget about being like provable, like to be able to really prove things. I mean, if you just want to discover new things, I mean, you have these enormous bounds, but you know, if you satisfy them, then if something is small enough or big enough, then you know something has to be 0. But if you forget about it, but just want to, let's say, discover new identities or things like that, and you don't care to prove that they hold using these bounds, can you maybe computationally just see if, like, has there been any experiments, just experimentally, to see if you can find new interesting identities and new conjectures and so on?
Well, so first, first I can give you a link to play around with. So I have to figure out where this chat room is. Where's the chat? Oh yeah, here it is. Okay, so first, so you can actually compute these periods. And there, for example, given a quartic surface, it just suffices generally to compute this periods to 100 digits. And then once you compute it to 100 digits, you can guess their integral relations, and you have the Picard group. on the node. So what I was saying is, this is previous work. For example, my previous paper with Pierre was about this, that you can compute this kernel of the period matrix very, very confidently. You use 100 digits of precision, you see you make like 100 digits of error. So, and you can use 300 digits of precision, you see again, you've made only that much error. And we have also other checks. Anyway, so once you know the Picard group, you know all relations amongst periods. That's what it parameterizes. So now the question is, if you had a very specific identity to check in terms of periods. So I'm thinking of quartics. I was interested in the geometry. So given a quartic, I want to compute this Picard group. I want to find out what kind of curves there are. And for this, the code I gave you will work. And in fact, I can give you 184. So I can give you 184,000 quartics where we've computed the Picard groups and various properties, the type of curves that appear. And this is also here. There are graphics and histograms and so on that you can look at, these 184,000 quartics. But now that's the geometric side. So what you can ask is, let's say, you say, I have two numbers and I want to say whether or not they're equal. Well, then first you have to figure out which quartic gave rise to these numbers. And this is an entirely different problem. So if you start with the complex number, then I don't know how to go to geometry. Typically, with these conjectures, you always remember the representation of the number, so that you write this as, x. You write this number as x, omega, and gamma, and you say, okay, I can always realize this triplet as a number. That's easy. You just take the integral, but you never talk about going back. So that's a huge missing chunk of this series of conjectures which Kontsevich and Zagier wanted. So one of them is precisely this. So you see with an algebraic number, this is not the case. If I give you an algebraic number, even approximately, and maybe I give you its height or something, you can reconstruct its minimal polynomial by essentially trial and error, but rigorously if you know bounds on its height. No such thing exists right now, and probably you will not live to see it. But from a complex number, which you know is a period, you construct a quartic. That, in general, that seems super high tech. We have no idea how to do it.
Yeah. So, any questions?